Okay, let's pick up where we left off. In the last video, we showed you the chemistry of cyclization, in which we take the linear form of D-glucose and go through a three-step process to make the Hayworth structure or cyclic form of the same sugar, D-glucose. The real most important thing that we said from the last video is the transformations that occur. One, we said there's an exocyclic carbon that's above the ring, so-called flagpole carbon. The other, and this is particularly important, is we transform a non-chiral carbonyl carbon into a chiral alcohol carbon. Notice I've added something here that we didn't have in the last video. It's an H. That's this hydrogen right here. It's still there. I just didn't draw it in because it's implicit in the structure. But it's important for moving forward for us to know that this new carbon right here, which is still carbon number 1, derived from the carbonyl carbon, is a chiral carbon. Now, let's get into this new video by looking at the following exercise. We did the chemistry of cyclization here. I want to have you do it again, except this time I want to point out that when we did it before, the carbonyl carbon was pointing down. Remember, I said that this thing can rotate around. It could be facing down like it is here, or it could be facing up. I want to have you draw the structure of D-glucose after we do the cyclization chemistry on this structure where the carbonyl is pointing up. See if you can do that and come up with the structure. Okay, I want to get into this, and I'm going to show you how I generally draw these types of cyclic aldohexoses. I always start by drawing a hexagon. That's a 6-membered ring. But this hexagon has to have one oxygen in the ring, and I always put it up there in kind of the northeast corner like that. The next thing I do is I'm going to draw the flagpole carbon like that. Now that's got a alcohol that, like I said before, it's kind of like a flag. It can blow around to the right or the left. It doesn't matter. I'll draw it to the left this time to just point out that it can go in either direction. Now, to finish this, we've got to add the alcohols in there. And I want to just start by pointing out that the alcohols are going to be like this. Why is that? Well, they were down here on carbon number 4, up on 3, down on 2. These are going to be the exact same way. What was on the right is going to be down. What was on the left is going to be up. And that's unchanged. So when I think about glucose, by the way, I always think about down, up, down at those positions. Now all that's good, but we haven't finished the most important part, and that is the chiral carbon of carbon number 1. Now with the carbonyl pointing up instead of down like it was up here, the alcohol is going to be also pointing up. And the hydrogen, of course, will be opposite of that, going down. So notice we still have a hemiacetal, which we introduced that term last time, but this time we can see a clear difference. In this case, the OH was pointing down. In this case, it's pointing up. It's the opposite chirality. That means we have yet another isomer of D-glucose. I know this is getting complex, but bear with me on this. Because these are both D-glucose, but they are not the same molecule, we have to have different names for them. And believe it or not, we are going to use the Greek letters alpha and beta again. This is alpha and this is beta. This has nothing to do with alpha carbons from amino acids. It has nothing to do with alpha helices and beta sheets. It's simply two different forms that we're going to call D-glucose. Now, if you haven't figured it out, this carbon that we're working with, let's label it very carefully here. That's really important. It is a new chiral carbon, and it was derived from the carbonyl carbon. And I'm going to give the name that we call this. This is called an anomeric carbon. And these two sugars are called an anomer pair. They're anomers of each other. It's another type of isomer, kind of like epimer or enantiomer. And they're both D-glucose. How do you know where the anomeric carbon is in a cyclic sugar? It's going to be a really important skill. I want to point out that an anomeric carbon is really easy to find if we know this rule. An anomeric carbon is always connected. If you look up here on alpha D-glucose, it's always connected to two oxygens directly. It's always connected to the ring oxygen and to the anomeric alcohol right there. Same thing down here. This is connected to the ring oxygen and the anomeric alcohol attached to it. All of the other carbons in a sugar are attached to just one oxygen. So that's a rule we'll go over a little bit later. Okay, one more skill and then we're going to stop this video. How do you determine whether a sugar is an alpha or a beta anomer? It would be nice if we could simply find the anomeric carbon and its alcohol and say, well, if it's down, it's an alpha, and if it's up, it's a beta. In fact, that will work most of the time, but it's not quite good enough. For one thing, we may draw the sugar upside down or something like that, and we'd have a problem. So what we do is, bear with me, this is a really important rule. We are going to have an internal reference. What we're going to do is compare the anomeric alcohol, which is the alcohol attached to the anomeric carbon, and the exocyclic carbon, which is number 6 in this case. Notice the exocyclic carbon is up and the OH is down. That's an alpha. If the anomeric carbons are on the same side as the high-numbered exocyclic, as we see down here, that is going to be beta. See, same side, they're both above. That's another rule that we'll write down and practice a lot later. Let's not worry about it now. I just wanted to make sure you understood that there is a clear rule for all of these things.